Binding energy and mass defect. Alright, so when you calculate the mass of when you calculate the sum of the individual nucleons, which is the sum of the individual protons and neutrons. Okay, in this case, we're adding the electrons. So if you add the individual nucleons and the electrons, you get the total mass. But then if you actually measure the mass of the atom itself, and you compare them, then the sum of the individual subatomic particles is greater than the mass of the atom. So this is just an example in the diagram. So if you look at the proton and the neutron and the electron, if you were to add them up individually, you get 2.016490 atomic mass units. And if you were to measure the mass of a hydrogen atom, you get 2.014102 atomic mass units. Now, you have something that's missing. So the missing mass is called the mass defect. So that is the difference in the masses. So you're missing 2.388 times 10 to the minus 3 atomic mass units. Now you can think of that as the mass defect, or as the binding energy. So what we mean by that is that this is the energy needed. 2.388 times 10 to the minus 3 atomic mass units. Remember, that's the units of mass, but we need to convert that into energy. But this missing mass can be converted into energy, and this energy is needed to break the atom apart into its individual components. So if you look at the equation beneath here, the bound nucleus, if you were to add energy to that bound nucleus, you end up with the individual nucleons. Let's just say that you got a brick, and then you have a hammer, and then you use that hammer to break that brick into. So you use force, right? You need to work. You need to apply energy to the brick to break the brick into its smaller parts. Now, if you were to reverse that equation, you get individual nucleons is equal to bound nucleus plus energy. Now the reason for this is because you have the strong nuclear force. Normally, if you have two charged particles, let's just say the same charge, the protons in the nucleus, they will naturally repel, but the closer they become, the attractive they become because of the strong nuclear force. So if you were to bring the individual nucleons very, very close together, eventually the nucleus becomes bound, and you will also release energy. Right, let's go through some terminologies here. So the notation is AZX. X is the element, A is the mass number, Z is the proton number. So Z tells you the number of protons. That tells you what element it is, because different elements have different number of protons. And A is the mass number, where it is the number of protons and neutrons. If you do A minus Z, that will give you the number of neutrons. Right. So the mass of a nucleus is always less than the sum of the masses of its separate protons and neutrons. So the number of neutrons, which is Z, Z is the number of protons. So Z is the number of protons times the mass of the protons, which is MP. That will give you the total mass of the protons, plus N. N is the number of neutrons times the mass of the individual neutron. So here is the total mass of the individual protons and neutrons. So if you write it in notation form, the mass of the nucleus is much less than the sum of the individual protons and neutrons. So this difference is known as the mass defect, the mass difference between the total mass of the constituent nucleons and the mass of the nucleus. So where has the mass gone? It has become energy, such as radiation or kinetic energy, released during the formation of the nucleus. This energy is known as the binding energy. So the term binding energy is the energy needed to break the nucleus into its constituent parts. So it is the energy needed to break the nucleus into its individual protons and neutrons. Right, so the sum of the masses of neutrons, this is mass defect, the sum of the masses of neutrons and protons forming a nucleus is more than the actual mass of the nucleus. The difference of the masses is known as the mass defect. And then we have the mass-energy relation, which is E equals mc squared. Einstein showed that the mass is another form of energy and can convert mass energy into other forms of energy. So E equals mc squared, c is the speed of light, which is 3 times 10 to the 8 meters per second. Right, you need to be able to draw this graph. So on the y-axis, it is the binding energy per nucleon, delta E divided by A, and on the x-axis you have the mass number. Now there is an optimum number. Usually that's iron. Sometimes it could be nickel, but it's iron. So here you just need to, when you draw a graph, make sure you're able to label the x-axis, which is the atomic mass on the x-axis. On the y-axis, it is the binding energy per nucleon, and uranium is on the right-hand side. The optimum, or the highest point, is iron or nickel, and here you can label it hydrogen and helium on the left-hand side. Right, so in physics, binding energy is the minimum energy required to either separate an electron from an atom or to separate the protons and neutrons of an atomic nucleus. Well, here when it says the binding energy, I think it's talking about the ionization energy. So it's quite similar. Ionization energy is quite similar to the binding energy. Right, the strong nuclear force. It is a fundamental force of the universe that allows subatomic particles to be attracted at short distances. It is this force that counteracts the repulsive force known as the Coulomb force. Now, the binding energy is not only the amount of energy required to break the strong nuclear force bonds, it is also a measure of the strength of the bonds holding the nucleons together. Because the bigger the binding energy, the more tightly bound that nucleus is. So if the binding energy for the products is higher when light nuclei fuse or when heavy nuclei split, either of these processes will result in the release of the extra binding energy. This energy is referred to as nuclear energy or nuclear power. It is observed that the mass of any nucleus is always less than the sum of the masses of the individual constituent nucleons which make it up. The loss of mass, which results when nucleons are split to form smaller nuclei or merge to form a larger nucleus, is also attributed to a binding energy. This missing mass may be lost during the process in the form of heat or light. So, by definition, the energy input equals the binding energy BE. The pieces are at rest when separated, and so the energy put into them increases their total rest mass compared with what it was when they were glued together as a nucleus. That mass increase is, because we're using E equals mc squared, we arrange E equals mc squared for m. M is equal to E divided by c squared. So the binding energy divided by c squared, this will give you the mass defect. So the more tightly bound a system is, for example, in the nucleus of an atom, the stronger the forces that hold it together and the greater the energy required to pull it apart. Right, so what do you need to include in the diagram? So this is a line of best fit, which is a curve. There is a bit of, obviously, this is just like, because this is a line of best fit. The graph line cannot start at 0. Make sure you write the numbers on the axes.